Hey guys, welcome back. Coach Nate here. We're going to talk a little bit about excitation contraction coupling with respect to muscles in the sliding filament model. First, a little quick introduction. This is my YouTube channel, so go ahead and subscribe if you're not, or at least check it out. Maybe set a like or a comment. That anything helps. You don't have to actually be a subscriber, but it would be awesome and appreciated if you would. Another thing about me is that I have a degree in kinesiology from Western Washington University, a degree in biology, and a minor degree in chemistry. So that's just a little introduction about myself. I'm currently working on my CSS. I'm a NASM certified personal trainer, and I work for Exos at Google as well as Blinnergy. So I work at multiple locations and train many clients. So let's kind of get into this a little bit. First of all, this is just my Instagram, so you can go ahead and feel free to follow me on Instagram. On both YouTube Shorts and on Instagram, I've talked about, muscle protein synthesis. We've talked about glycolysis. We go into the biochemistry of, the connections to kinesiology with biochemistry, like the mTOR pathways, the AMPK pathway, how those things interact, how they make muscle growth and fat loss interact, all that stuff. So go ahead and check it out there. But for now, let's get right into our video. So we could write an entire book about this stuff, or let me know in the comments if you have any additional questions. But for now, we'll go ahead and start with what I've got here. Apologies for my horrible drawing skills. But anyways, first off, we've talked about motor unit recruitment already. You can check that out on YouTube or on Instagram. But what happens is after your brain decides which muscle fibers to use, then you have the actual physical mechanism that causes contraction. So this is excitation-contraction coupling. What happens is you're going to have your action potential that was sent from your brain. It's going to release these acetylcholine molecules onto the sarcolemma from the neuromuscular junction here. That's what this little circle is. This is the neuromuscular junction. So it's going to shuttle these acetylcholine little circles down into the sarcolemma, which is just the surface of your muscle cells. This little guy right here, I'll go ahead and put in a little binding site here. Once enough acetylcholine binds to these little receptors, acetylcholine receptors on the sarcolemma, that's going to generate an action potential, which is an all or nothing thing. So it's like if you reach, if you reach negative 55 millivolts, right, so you're putting a positively charged, molecule here into these ligands to make the resting voltage, which is usually around negative 90 or negative, I've seen in some textbooks negative 70. I don't know how outdated that is. It's probably negative 90. It's going to make that go up to negative 55. And if it's negative 60, negative 56, it's not gonna happen. So negative 55, that's the all or nothing, okay, now we're gonna go. So we got to negative 55, boom, you're gonna get all this voltage happening. It's gonna run through the sarcolemma, go down these T tubules here, and then you're gonna activate these voltage gated ion channels, which are gonna release calcium. So calcium is another positively charged ion. All right, so why does that matter? And how does that relate to contracting your muscle? So let's get into that. Now, your muscles, you have what is called the sliding filament model. Let's go ahead and erase some of this stuff if we can. Okay, cool. We can just have a new thing here. So what's going to happen when that calcium is released? I'll show you more in depth, the biochemistry behind that in a second here. But let's go ahead and take a look at our sliding filament model. So inside of the muscle cells, we've got these little units of contraction called the sarcomere. All right. So on these sarcomeres, you've got these are myosin. I'm horrible at drawing. I'm so sorry, you guys. In the middle. All right. There we go. Boom. There we go. Cool. And then out here, we've got our actin. So I'll just draw a few of those guys. Just lines of actin here. And the idea is that when this calcium is released, it's going to bind to troponin, which is a molecule that's kind of tied to this little tropomyosin molecule. So this little thing that's kind of blocking all of the myosin from attacking these binding sites on the actin. And what's going to happen is that calcium binds to troponin. So this molecule it's a complex of like 3 separate molecules that work together. So there's troponin I, which is actually binding to actin. Then you have troponin C, which is what the calcium binds to itself, and it's going to change that conformation of that molecule, which will then cause the I to stop binding to actin so tightly, so myosin can kind of go there. And it also moves out of the way of the myosin heads. So, and there's troponin, I believe, T, which is tropomyosin binding troponin. Anyways, that's what kind of sticks it to the tropomyosin. After the calcium binds to our troponin on tropomyosin, it's going to cause this tropomyosin to move out of the way of the myosin globular heads. So I think if I just go undo, we can get rid of our tropomyosin. There we go, it's gone. And then these little myosin heads can go ahead and bind to actin. What's going to happen is using ATP, the energy currency of the cell. So it's literally just like 3 phosphate groups on a adenosine molecule. So I'll just do like a little that for now. It's not how you draw adenosine. But anyways, or actually I don't know if you can see that. Let me draw it over here instead. So we got 3 phosphate molecules on our, I'll just draw an A for adenosine with a big old box. Cool, so there's our ATP molecule. That right there is going to bind to our myosin, and then when it breaks, that releases enough energy to cause the binding to actin, and then it's going to pull actin this way, and these ones are going to pull actin this way, which is going to shorten the sarcomere. So that is how you actually contract your muscle at the most basic fundamental level. All right, cool. So we've seen that. I hope you enjoyed my horrible drawings and my super fast talking. That probably didn't make sense. So what is acetylcholine? So let's kind of talk about that. Acetylcholine is a molecule. It looks kind of like this. Let's draw it. I'm on like a ChemDraw online thing. We're going to need to put a nitrogen right here. And it's a positively charged one. And it's actually got 3 methyl groups attached to it. So it's going to kind of look like that. I'm pretty sure that little red line just means it's positively charged. Let's go ahead and I wish we could add a little plus. I'm sure we can. Maybe if we go like this. Okay, yeah, there we go. Great. Positively charged. Great. Then what we're going to do is we're going to go ahead and add our acetyl group. So it's acetylcholine, right? So let's go ahead and put that on here. It's going to look like that. And then it's attached to another. Oh, so sorry about that. Hold on a sec. Go back. Great. Let's move our group over here, and then we'll have our little oxygen double bound to this group here. We'll get rid of the alcohol group. Do a little reaction here. There we go. Okay. So this is our acetylcholine molecule. This is like not a great representation of it. I wonder if I can move this, tilt it a little bit. Okay, that's marginally better-ish. And then we can move this one. Can we move that? That's fine. Okay, this is a horrible drawing here. Anyways, you get it. That's acetylcholine. So that's going to bind to those ligand-gated ion channels, which then cause those voltage to increase, and then your voltage is going to cause those voltage-gated ion channels that release calcium to open. So after we've released our calcium, it's going to bind to troponin. So this is actually what troponin, the molecule itself, looks like. Like I said earlier, it is a 3-molecule complex. So this little blue area here, this is troponin C. This is actually where the calcium is going to bind. That calcium is a positively charged ion, so it's going to look for negatively charged groups. So as you'll see in here, okay, right over here we've got a glutamic acid or glutamate amino acid, and if we actually go to the ball and stick model instead of the cartoon model that shows the alpha helices, you'll see here we have a glutamic acid or glutamate amino acid right here. So on the negatively charged parts of this, you're going to get your calcium to bind on the binding sites made up out of all of those negatively charged groups. Now, what happens when that happens is that you kind of get a neutralization happening, and it allows all of those nonpolar molecules, which are hydrophobic. Remember, the cell is made of water for the most part, right? So we're going to cause a conformation change by those getting neutralized, and then our water-fearing groups are going to have their time to shine. They'll come out, and that causes a conformation change. So right here, we've got a phenylalanine. There's a lot of these that are kind of tucked away behind, and they kind of come out after the calcium binds. So that's how your conformational change is going to look. Some of our molecules kind of disappeared. Let's put it back. There we go. So that is troponin C, where calcium is going to bind. It kind of looks like two little arms coming out. Let's go ahead and put our cartoon back. Okay, so there we are. Now, next over here, we have our troponin I. This is actually going to be what's just binding to actin. So it's literally on actin. It's just a binding site. And then over here in the green, this right here is our troponin T. So that's what's bound to our tropomyosin molecule. So that is kind of how troponin works. It's really important that you know that, because of this is where the calcium's going. This is going to be causing a change in this molecule in your muscles, and then this thing moves the other thing out of the way, and I'm going to show you that next. So right here, we actually have our myosin heads. So this yellow and brown, they look kind of like golf clubs, right? The myosin heads on this model, I believe this is like an active model, so they're bound to the actin already. But so that troponin had a configuration change, and now this tropomyosin has moved out of the way. That's these little like helice looking things on the outside. So like the blue and the green here, and then the red and the gray here. So right there, you have your tropomyosin, and that's kind of surrounding your actin molecules in the middle, which are also making kind of a helix. It's just like they're more bead-like. So you can imagine that this is long, right? Okay, cool. So let's go ahead and look at this a little bit differently. So we want a ball and stick model. We can look at that. And then we want a Gaussian surface model is the much easier to look at. There we go. Okay. So now that we have the surface area model, it's much easier to look at. You can see kind of how this works. This actual physical objects grabbing onto each other, binding. These myosin heads are going to make their stroke after another ATP molecule is used for energy. You're going to go whoop, and then they're going to crawl this actin that way. And then you're going to get your muscles to contract. So this is like the literal actual molecules. This is the biochemistry that is happening when you are contracting your muscles. So that's what I'm talking about when I talk about the power stroke, or when I talk about the sliding filament model. Like, this is the very bare bones, like the bottom of the barrel. This is what happens literally at the molecular level. Okay, so these are protein complexes. I don't know why all the actin is a different color, little rainbows. Then you've got these myosin heads on the outside, and again, that tropomyosin that was blocking the myosin because of troponin. So tropomyosin, the name makes sense. It's all right there. Okay, let's go back to that sketch pad and go through this again. So you have your thought about you're going to go lift something. Then you have your motor unit recruitment, which we already have a video about. You can go look at that. And then this is again called excitation-contraction coupling. The excitation part just comes from excitable cells, which like muscle cells and neurons, because of the action potential. Okay. So that's what this is all about. And also probably because of ATP or coupling ATP to like literally causing mechanical work. So anyways, I hope you guys liked this kind of introduction video into excitation, contraction, coupling. And I hope to see you guys in the next one. Please subscribe if you're not. But again, you don't have to. But check out maybe my YouTube channel and my Instagram. I do a lot of fitness content, and we're going to do a lot more science education as well. Peace.